Hello.
Hello, good morning, Bang Bang Con. Um, oh my goodness. Hi.
Hello. My background is physical and not digital, which means
Oh,
that
really?
if it's in the wrong position, I need to move it.
Uh-huh. I have a kind of janky setup this morning, although not as janky as it was last night. That in particular, I have a two laptops set up here that I have my big screen that I'm like reading all my notes from up here,
Mhm.
but actually Ertie is down there. And so I have to like it is very weird. I'm used to this universe of making Zoom eye contact by looking at the person. Um,
Yes.
and but now I have to remember that that won't work.
Yeah,
So
I
now
can
that I
look up
have,
here. That's where I should be
okay,
looking, even though you're
okay,
all the way down here. Yeah, exactly.
that's right,
Exactly.
exactly.
There's like a
Um,
weird we're all like as a society like figuring this out, right? Like where do you look during, during a meeting, during a Bang Bang Con broadcast, right? Well,
right.
and then I have some coworkers whose camera is off to the side, for example, and so
Hmm.
when they're in the meeting,
Hmm.
they're looking like this, and they're looking at you,
Right. Yeah.
right? Yeah.
Yeah. I used to have this problem also. Sometimes like OS 10's USB video stack is not very robust, and
Hmm.
my USB webcam on this machine sometimes decides that it like shall not like it does not wish to play,
Yeah.
and so I have to use my actual laptop is over here, and the but my big screen is in front of me, and so I end up looking like this, and with like a very grainy image from my built-in webcam. Um,
Yeah.
anyway, I have a Bang Bang Con story to tell this morning.
Please.
I went on a little adventure over the past couple of days. Um, I I use at my desk here for audio stuff. I'll show you. I use a Blue Yeti, which is I love this. I love the microphone. I love the way it sounds. It's a great microphone. Um, and so I found I had a very cursed problem, which is that on Thursday night my microphone lost its firmware.
That's
That's
very
a weird
cursed.
sentence.
That's
That's
cursed. Yeah.
yes. Um, I was using it to dial into a call, and I plug it into my laptop, and it doesn't. Something goes wrong, and I unplug it and I plug it back in, and instead of showing up as Blue Yeti, it shows up as USB Advanced Audio Device by C Media Corporation, um, which is a very odd turn of events. It has lost its name. It has lost its identity. And in dmessage, it told me what it was before and what it is now. So I saw the old Blue Yeti descriptor, and I knew that
Okay.
this is not normal. And so it turns out that the microphone uses this commodity USB chip that has a attached serial EEPROM.
Okay.
Um, and the serial EEPROM can sometimes like lose bits, like something can go wrong. Um,
Okay.
and it turns out this is a known phenomenon. So I mailed the people who make it Blue, and I said, can I reflash this myself? Like I have many computers here,
Yeah.
and they were like, no, you should RMA it. And I was like, well, that's not any fun now, is it? Um, and so it turns out that this chip has a mode that you can talk to its EEPROM over. It has an I2C EEPROM. You can talk to its EEPROM over USB.
I,
Um,
I assume for like remote updates and
Well,
like.
for initial programming, I believe,
Oh, okay. Okay.
because there's not much interesting in the firmware, as it turns out. It just
Okay.
contains like some descriptors and some config files about like equalizer settings and gains.
Mm.
That's why I really wanted it to be working.
Okay.
Like I wouldn't care about the name otherwise, but the equalizer settings and the gains I want to be right. I want it to sound right.
Yeah.
Um, and so I found this like Windows blob CM64XX config.exe that could read the EEPROM out of the thing. And I found some guy who described in like rapid fire Spanish on YouTube how to fix this. I was
That's
like,
amazing.
okay, time to page that back in, right? um, and so I use this tool, et cetera, et cetera. And I was like, well, I need a known good firmware from someone. And I don't want to like make my friends run this sketchy Windows tool. And so I spent the afternoon in Ghidra like disassembling it. And I figured out how to talk to it over HID. And I wrote a little HID API tool. And I was like, well, we could do one better. I bet browsers can do this now. So if you look in pound
like
random on Discord.
Yeah. Okay.
If you look in pound random on Discord, I have a web HID program that will dump the firmware off your Blue Yeti if you have one attached.
I see that, yeah.
You just click on it, and then you click on your microphone, hit allow, and it goes, and it reads the firmware off of it.
Okay. Does it make that noise while it does it? Because that would be amazing.
It ought to.
Yeah. Anyway, sorry, keep going.
it does have a spinner. It has a spinner that bounces.
Okay.
But because it takes like just long enough that you're like, is anything actually happening? But yes, it will do that. And I then wrote a function to write to the I2C EEPROM. And I found that like exactly 2 bytes had been corrupted. And that was enough to cause the USB chip to get angry about this. And so right now so I patched those 2 bytes, and as you can hear, my microphone works now.
Yeah, that's amazing.
I'm very excited. Maybe I should have saved this. This is a USB story. Maybe I should have saved this for before Kate Temkin's talk.
I really think you should have just saved it for next year's Bang Bang Con and submitted it as a. Oh well, actually, you just gave a Bang Bang Con talk. I just want to point this out to you. So
I gave a Bang Bang Con talk last year. That's right.
Bypassed the.
Sure. That's right. I've that's the I submitted a talk this year and I didn't and there were so many better talks this year that I'm always happy to be rejected from Bang Bang Con.
Just to point out that our anonymized submission process is truly anonymized. Like even I also have had my talks rejected from Bang Bang Con. So
are you as excited by it as I am?
I mean, well, it's kind of. I mean, it was funny because like my talk, we do like this like graded talk proposal. You can read about it on my blog. And my talk got B's across the board. So like nobody, I didn't even get like one champion. So I was a little less excited. I mean, I was excited that like the anonymized, like proposal worked, and nobody was like biased for my talk because I'm an organizer. But I was a little down because like I didn't even get one A. But that's okay. It's good feedback. It's very good feedback.
Yep. Okay. Well, it's on the West Coast here. Oh goodness, I may have to sneeze. Uh-oh.
Well, in that case, I will take it. So we're 10 minutes after the hour. This is session number 9 of Bang Bang Con 2021, and our first speaker is Laura Korup, and the talk is Geometric Derivations of RGB Color Space: The Strange Eyeball Science That Is Messing with Your LEDs. Laura helps public sector organizations deliver on their mission in innovative ways by unlocking the value of data. Outside of work, Laura expresses code and data as tools to make art, find new perspectives, and connect with community. When she's not debugging her latest Python project, Laura is probably canoeing on a whitewater river or falling off her skateboard.
And I guess we should do the before Bang Bang Con notes also.
Oh my gosh, I'm so sorry. I skipped straight to the. I just got so excited about these talks.
Yeah, right. I know. I'm really excited about this talk also. But okay, we have some sponsors. Go ahead.
Yes, let's introduce our sponsors. Sorry, Laura. My B. Go ahead.
Okay, so we have excellent sponsors this year. Excellent. Xander and Daily are excellent sponsors this year. We have some awesome sponsors this year. Wherewithal, who is also sponsoring the live captioning that you can see right below here right now. That is a real live human. Mirabai Knight is busily typing on a very special keyboard. So Wherewithal sponsored that. We have Discourse as a sponsor, Full Story, 2 Sigma, Phase Zero, Mapbox, and Accelerated Tech. And if you want to tweet about Bang Bang Con, you can mention at Bang Bang Con, but we have some amazing K-pop stans who have taken over hashtag Bang Bang Con, and there is a article about this, and I'm not going to delay Laura's talk anymore. We can talk about that later.
Okay.
But you can use the hashtag virtual Bang Bang Con to tweet about us. And All right. And
All right.
now I think I've said everything that needs to be said. Let us begin. Good morning, Laura Krupp.
Hi, good morning. I'm going to be talking about LEDs and eyeballs today. So I am not an expert in either of these topics, but during the pandemic, I discovered building hardware and electronics. It all started with a kit to assemble this clock. I didn't really know what I was doing, but I was fascinated and I loved looking up what every piece was and trying to understand as I put this together. I've worked in data and technology for a long time, so I've written a lot of code that's in web apps, websites, data pipelines, but they're all a little abstract. And when I close my laptop at the end of the day, it's not tangible and in my living room. So this was magical to me and led to all kinds of ideas, most of which I haven't built yet, but I'm diving in to create interactive physical things. And most of them for me come back to color. Unfortunately, turns out this was a little tricky and I was really confident that was going to be an easy part and I definitely ran into trouble. So today I'm going to share with you a quick refresher on the basics of LEDs, where I ran into trouble, 3 specific spots, and then what I learned on my journey to understand. So this is a RGB LED. And you may have seen them like this as well. They're very common today in strips. And if you get the right kind, you can control each of the LEDs individually, setting brightness or color. But all of these, whether the former or the latter, actually have 3 lights inside every LED, a red, green, and blue. Turns out this is all you need to make millions of colors. So I hooked up. This was my first time hooking up my RGB LED. I'm ready to go. And this is how you set values, not the color picker on the right, but setting values for RGB. It's typically a number between 0 and 255. And you would set that for red, green, and blue. That's because one 8-bit byte holds 256 integers or 0 to 255. So that's the way we've always stored these values. And it lives on in color pickers like paint and other things you see. So I'm ready to go. I'm ready to move through my millions of colors, and I think I'm going to hold brightness or luminance steady. And so this should be easy, right? I'm just going to slowly decrease red as I increase green, and so on and so forth. And I think as I do that, I'll get this nice color fade. I'll do the same with green and blue. So here was my code, pretty simple. Every 5 milliseconds, I am rotating through and I'm going to be decrementing one color until it's 0, while I increment another color until it's 255, then switch to the next set of colors. So this definitely gave me some glowy gradient, but it wasn't quite what I expected. The weirdest thing is it seemed to pulse with lightness at different times. I thought I was holding the brightness steady. So the brightness seemed to vary when I was only trying to change the hue. So, okay, well, these colors kind of looked washed out. How can I get the colors I really want? Well, there's all kinds of RGB color pickers online. And as you can see, they're not all constant brightness. To create navy or dark blue, you need to have much lower values. This was my first clue that brightness is intrinsically tied to color and you can't separate the two. And this means there are a lot of optical illusions where 2 colors that appear to be the same brightness, if you grayscale them, they're drastically different, but it's because of how we perceive brightness for that color. So at the end of the day, it was still hard to create the hues that I expected. And so I started building more clocks. I was on this path to build clocks, and I've used a bunch of different digits. These are, a maker built these, and they're on rgbdigit.com. You can find them on Tindy, different people putting together RGB LEDs into different combinations of digits. And I wanted to do these beautiful gradients. So maybe at sunrise every day, there would be some kind of animation, and the clock could be bright, vibrant blue colors during the day. And overnight, so it wouldn't screw with my night vision, it could get deep red and orange. So I did a lot of manual color picking, but at the end of the day, I programmed the clock during the daytime and I just scaled everything down linearly to the brightness I wanted at night. And it didn't look good. There were things that the color wasn't what I expected, or where I had a refresh rate where I was updating the color. You couldn't perceive it with the naked eye at all when it was bright. All of a sudden at midnight, I could almost see it flickering. What was going on? So there are libraries that fix this, but I want to talk a little bit about what the problem was, because it wasn't my code and it wasn't my hardware, which I did wonder for a moment. Turns out this is actually how we perceive color. One note that as much as 1 out of 8 men and 1 out of 200 women have some type of color blindness. And so while that's important to remember, certainly for design and communication, there may be folks who don't see this presentation the same way I might. So here's what I remembered about the eye. There are cones and rods, right? And this is how I imagined them. And even though there are millions, I'm like, okay, these are sticking on the back of my eye. And that's about as much as I remembered. Well, it turns out rods actually look like this. And there are around 120 million of them. And there are around 6 million cones. I also had imagined, and oftentimes you'll see it oriented this way in papers or books, that the cones and the rods were the thing the light was hitting first. Turns out that's upside down, and the light actually is passing through this layer of nerves and nerve cells before it gets to those photoreceptors. They're also not distributed evenly. Right in the middle of our eye, we have a really extreme density of cones, and the rods are more on our peripheral vision. My favorite way to play with this, if you haven't tried this, is when you're looking at stars, you can often find a star in the sky that you can see it out of your peripheral vision. If you look straight at it, it disappears. Look just to the side, it reappears. And that's because it's too dim for your cones, which are in the center, but your rods, your peripheral vision, can see it. So one thing to know about the cones, these 3 photoreceptors we have in the back of our eye, is that they are sensitive to different ranges of wavelengths of light, and they even within those have different sensitivities. And this is part of what explains that glowing brighter, glowing dimmer effect I saw when I was blending linearly through the colors. The trichromatic theory explains why these 3 types of cones in our eyes can see millions of colors. So if we have orange and an orange wavelength is coming in our eye, it's going to excite the red cone, the long wave sensitive cone, and what we often call the green cone, the medium sensitive cone. These are made up numbers. Let's call this percent excitement. But let's say it's going to excite that long wave cone around 50% and the short wave cone around, or the medium wave cone around 10%, and it doesn't hit that short wave cone at all. That's orange to our eye. 50% excitement of the red cone and 10% excitement of the green cone, that equals orange. That means that we can recreate this lots of different ways. So to create orange in the RGB LED, we would be putting in a lot of red and a little bit of green, but to our eye, that equals the same thing. So I'm not going to go into the details on this, but part of what I found fascinating was metameric colors are colors that don't match the actual wavelength on the spectrum, but are built different ways. And you can definitely go into a deep Wikipedia hole on this, but there's all kinds of interesting failures where you match colors under certain conditions, but then if you look at it from an angle, illuminate it with a different light, you can actually see it differently. There's one more theory that's really important to understand, and it explains how we see an after image. If you've ever seen those optical illusions where you stare at the thing on the right and then you look away to a white screen, but you see the thing on the left, that actually is happening because of how our photoreceptors are connected to our optic nerve through these bipolar cells and ganglion cells. They actually kind of work like logic gates. So all cones can provide input into luminance, but there are 2 separate systems called the opponent systems that help those nerve cells actually interpret what it's getting from the cones. So we can either perceive excitement as red or green. We can't see both at the same time on that particular group of cones. Same thing, we can see blue or yellow systems, but not the same at the same time. This is why you can see reddish blue, but you can't see reddish green. It actually turns out that a lot of color is really dependent on context. So here, the top center square and the front center square are actually the same color, but our eyes are really good at trying to figure out what the lighting conditions are and then making assumptions based on that. Here's another, A and B are actually the same color. And even when we connect them, it's hard for me to believe that. I almost see that as a gradient. Color can also depend on the language you speak. Some cultures have more names for something that we might think about as light blue or dark blue, or less names, and folks will actually see those as distinct colors or associate different meanings with them where we may not see the distinction. So back to the problems I had, brightness seemed to vary when only changing the hue. It was hard to create the hues that I expected, and things that looked good when bright were bad with dim. The stuff that I learned is that perception of hue is tied to luminance and context, and you cannot disentangle those. Our perception of brightness is not at all linear. Our eyes are much more sensitive at low lights because of the cones, and not all humans perceive color the same way. So a couple of things we can do to fix these. The first is gamma correction. So this is linear intensity, but to my eyes and likely to yours, the step between 0.0 and 0.1 seems to be a lot bigger jump than from 0.9 to 1.0. So if we scale intensity on a logarithmic scale, we can get it to look linear to our eyes, even though it actually isn't. Humans have also tried to solve for blending colors by creating color spaces. So if you map RGB onto a cube, you can get this. The problem is it transitions between the colors won't actually look linear to the human eye. The color wheel picker is really popular today too. There's HSL and HSV. That's another way to pick color, but it's also linear in a way that makes sense for RGB, but doesn't make sense to our eyes. So there's been color standards, committees, official government colors, all kinds of ways to try and get us to agree on what yellow is yellow. Tests that we've run to display lights of different colors and have people say when they're accurate. And then there are color space development. So the International Commission on Illumination created a color space in 1913 that's still used today. It's 3D, and it allows us to measure the distance between two colors and to plan a path to fade between two colors in a way that looks a lot more linear. If you take away the brightness dimension, you can look at this in a 2D space. And when you map the RGB color space onto the C-Lab color space, you can actually see that the RGB didn't look very linear to the human eye. And this is a better attempt to do that. One final color space, and this is a new one. It came out in 2020. You can Google it, and if you just Google OK Lab color space, you'll find it. There's a lot of ways to engage with it in different programming languages, but it has 3 variables, but it works on predicting how to fade color, how to translate color in a way that is going to match human perception. So here's the rainbow gamut using OK Lab. And on the bottom is using that hue saturation value, which actually doesn't look like it's holding a constant lumosity to the human eye. It also helps you blend in between colors without getting too warm or too cool or blending too fast. So at the end of the day, what I'm now doing when I work with LEDs is I'm making sure I do gamma correction for the nonlinear perception of brightness. I'm still manually fine-tuning to pick my favorite hues, that exact color of purple or red that I want. But I'm using a color space model to figure out how to fade between colors in a way that's going to look good. I am testing separately in different lighting conditions because stuff just gets weird when it's dim. And in a lot of my designs, I'm thinking about how would this look like to a colorblind person? How would this look given some of what I've learned around cultural significance of color? At the end of the day, I know a brain is not a computer, but I've started thinking of these rods and cones more like sensors. They have a set of inputs they work very well for. They also have limitations. And then all of these cells they're connected to before they even go to your brain is like a microcontroller with some logic on it. At the end of the day, that impacts how we can see color, gives us this incredible adaptive ability, and lets us do really cool stuff with LEDs. Thanks for listening, and I'd love to connect with you either on Discord or Instagram or Twitter if you have any questions. Thanks.
Color.
Oh, thank you, Laura. Oh my goodness. So I used to like professionally do camera stuff. Like that. So color science is like tangential to what I would do. And I had like a vague understanding, like I had a conceptual understanding of a handful of things. And so one of my favorite things, like one of the things that I love about Bang Bang Con talks is and especially I think like Laura really exemplified this of one, providing great information to people who know nothing about color science. And two, to people who have been like steeped in the field or who have had tangential exposure or all this sort of stuff, also giving jumping off points for like more things to look up. So like I knew about Scilab and I knew like of that as a color space. I did not know about OK Lab. Like, this is brand new to me. Now I have some Wikipedia work to do later today.
People were like dropping links in the Discord, myself included, to just like all sorts of weird color related, like magenta, the color that doesn't exist, you know, like yeah, it's great. The whole thing about the neurons, like the antagonist thing, like all like several things about color that have mystified me for years, like all of a sudden I have this I don't know. There's like suddenly I like know where to go start thinking about these things. That's so cool.
I when I was working on this sort of stuff, I had a actually coworker, and so whenever somebody would say, "Well, the eye perceives it this way, and so we should do it this way in our camera," he would go, "The human visual system actually perceives it that way." And this is and Laura gave so much kinder of an explanation of why it is not just the rods and cones, but all of the weird processing that the brain does also.
Yeah.
Anyway, that was fantastic. I am very happy that we had that talk this year.
Yes.
Okay.
I want to point out the chat is like already starting for our next talk, so I feel like we should just get into it.
Yes,
we can talk about
I think that's the case. I think that's the case.
Interview later. Yeah.
All right. So coming up next is Kimberly Wilbur, who is continuing our theme of Doom Con. By talking about how layers upon layers of hacky abstractions turned Doom 2 into the best kart racer. Kimmy is a trans engineer in New York City. She likes to read books, sip tea, and work on Doom mods. All right. She's been a part of the SRB2 community off and on since 2003. Welcome, Kimmy.
Hi, listeners. I'm Kimmy. I'm a trans girl from New York City, and today I want to share a video game that's been really special to me. A game that's grown up alongside me, so to speak. See, this is a game that's been not so much developed as lovingly cobbled together from the pieces they had over the past 30 years. It gives it a really lovely charm. I'm talking, of course, about the very simply named Sonic Robo Blast 2 Kart, affectionately known as SRB2 Kart for short. SRB2 Kart is an open source, extremely customizable racing game focused on fast-paced gameplay and twitch reflexes. There's lots of ideas that make it special. The predictable and fair physics engine, the robust multiplayer capabilities, this power-up that chases you. It's half blue shell, half anxiety trigger. But the most charming aspect of this game, and the aspects that I wanted to highlight today, is how gosh darn customizable it is. That's right. This here is a Sonic the Hedgehog fan game, which means the entire thing is kind of one giant lovingly crafted shitpost from top to bottom. The community has put together hundreds of custom maps and characters, probably touching on every obscure anime character or pop culture reference that you can think of. You want to play Hatsune Miku? You can play several different versions of her in any selectable color. You want a literal office chair? You got it. You want a replica of the Hornet racing car from Daytona, USA? You got it. Well, it's a kart racer, you see, so it has to be a kart. The rally car is driving the go-kart, you see. So, interestingly, that's not even the most horrifying bit. All of this, right now, is running on a heavily modified Doom engine. Yes, that Doom, from 1994. Listener, it's 2021, and bless, we're still using the same file formats. Our mapping editors are writing the same data structures on disk with broadly the same constraints and limitations. Unsigned 16-bit integers are still everywhere. How did this happen? Dear listener, let me take you on a journey back through time. It's 1994, and Doom 2 was just released. One of the things that made Doom unique is that it was one of the first truly 3D games, but that's not entirely true actually when you look at it. Because despite the sophisticated graphics at the time, the levels were simple and completely two-dimensional, just like an architecture blueprint. I'll talk a bit about the level format in a bit later, but originally, Doom couldn't contain buildings with multiple floors on top of each other. It was fake 2D. And because of the straightforward format used for asset storage, it wasn't long, of course, before the community began reverse engineering its secrets. It turns out that the structure of Doom makes modifications super easy. If you want to replace all of the enemies with Seinfeld characters, for example, all you have to do is load a patch file that you downloaded over your modem that overwrites the enemy graphics. It's a different time before the internet. But eventually, id Software released the Doom engine as open source for non-commercial use. This made Doom an ideal development platform for many young game designers' overly ambitious fan projects. Like what, I wonder? Meanwhile, we had Sonic Roboblast. In many ways, SRB2 Kart traces its development history to this specimen from 1998. It looks silly, but I mean, come on, you could play as Sonic the Hedgehog on your computer, your IBM PC. It's incredible for its time. After this release, game designer Sonicu and his friend SS and Tails decided to base their next project off of the hot new Doom engine. They wanted to bring it into the third dimension. They called this Sonic Roboblast 2. The earliest versions from 1999 were more Doom than Sonic, really. They still had the characteristic gray palette, narrow hallways. It was Halloween themed, so you had spooky enemies still, which were little more than MS Paint scribbles, of course. But it was a start, and it soon grew this small cult following, which then blossomed into like a vibrant community. For all its faults and toxicity, the SRB2 community is special to me because it was really my first online community that encouraged aggressive self-expression. I could see all the zany characters and original creations that my friends were making. To paraphrase Toaster, one of the SRB2 Kart devs, you had all these creative kids who were hungry for their Sonic the Hedgehog content back in 2004, and you had this really malleable game engine. And as long as the environment isn't too aggressively toxic, what happens is that, this game, SRB2, is ideally positioned to kind of absorb as many kids as possible into a swirling mass of unrefined creative talent. Back then, messing around in the level editor and excitedly posting my terrible creations to the message board kickstarted my computing career, honestly. And of course, I wasn't the only one. Before long, modifications to SRB2 started popping up on the message board like wildflowers. Some good, some bad. For the ones related to SRB2 Kart's history, going through them really quickly, you had MK Races. This is one of the very earlier ones, July 2005, I think. It's pretty primitive. You are instantly killed the moment you fall off the track, for example. Moving on, we had SRB2 Riders in 2006, I think. It's a parody of the Sonic the Hedgehog skateboarding game. It also had an extra kart mode, almost as an afterthought. People ran with that one. You had Dude Kart 64, Super SRB2 Kart Z, and all of these other efforts done by other creators on the message board. And that sort of coalesced into SRB2 Kart that we know and love today. Meanwhile, the Sonic Roboblast 2 video game itself also matured into a very high-polished release. The two games have heavily overlapping, but kind of slowly bifurcating communities with a distinct development focus. It's really fascinating to watch given their humble origins. So, in short, SRB2 Kart is an amalgamation of an overhaul of a joke gameplay mode inside of a mod of a Sonic the Hedgehog total conversion of a Doom source port. 1994 to 2021, all right here. But for everything that's changed, things are broadly still the same. In 1994, Matt Fell wrote this amazing giant text file, the unofficial Doom spec. one of the first efforts to reverse engineer the system. And almost everything written here still works the same. Let me give you a comparison. This here is E1M1, the first level in the first episode of Doom. As I mentioned earlier, Doom levels are stored as 2D architecture floor plans. You have vertices, which are 2D points within each map. You have line defs, which connect pairs of vertices. Each line here has a front side and a back side, each of which might be textured. And connected lines form sectors that the players can walk through. It's all indoors. To provide the illusion of 3D gameplay, you can raise or lower the ceiling on each sector floor so it comes into or out of the screen in this top-down view. That way you can have some height. You can make rooms and stairs and ledges, which give a bit of verticality. And then finally, a list of things like monsters and power-ups populate the objects within each level. That's all there is. Nothing more, other than the graphics. This map was made in '92, I think. It's fairly famous. Compare that to, this is Splashdown Zone, a recently released cart level from a mapper named Ivo. I'm opening it in exactly the same tool. It uses the same binary format, the same conventions. As before, you have your vertices, you have your line defs, you have your sectors, except in-game, this is what it looks like. A sprawling canyon dash through a vibrant outdoor landscape. The same primitive building blocks, transforming those bloody, dark hallways into something fresh. A reframed space that's new and inviting somehow. That's what makes this game so special to me. After all, SRB2 Cart is, like us, lovingly cobbled together from whatever pieces we have. Thank you.
Oh,
That was beautiful. And I believe we have Kimmy online here.
Hey, everyone.
Hello.
hi, Kimmy.
Hi.
Oh, that's fantastic. That's so good. I'm so glad.
Did you have something in particular, or did you were you just hopping on to say hi and?
No, I'm just saying hi. Hope you
Okay.
liked the talk. Go play SRB2 Cart.
Yeah.
Unless it crashes on your computer. Sometimes on modern computers it crashes a whole bunch, which is always fun because all the code is from like 1992 that has been changed into 1999 and changed again throughout 2015.
Can you run it on like, I don't know, DOSBox or something, or are you just
DOSBox?
Good
No,
luck.
so these days it works on Windows, Mac, Linux. There's an Android port of the original SRB2 game, but not the cart game.
Okay.
So it does run on modern systems.
Okay.
I was going to wonder, I was about to ask whether this like works with all of the Doom, like whether the Doom engine is changed or whether other things, whether it requires changes inside the Doom engine. You can't just run it on any old Doom core. I'm going to save that for Discord. I'm going to save that one for Discord.
For example, are a feature that required a rewrite of like half of the Doom engine. The original Doom engine doesn't support slopes. And so not only do you have to figure out how to represent that in the level format, but how to render that efficiently in both the software and the OpenGL renderer. That took a lot of linear algebra. It's quite incredible the amount of love that has been placed into modifying the Doom engine to support all these special effects.
I love how these things we take for granted, like slopes, are like incredibly difficult in 1992. All right. Well, thank you for hopping on. Thank you again for your talk. And let's.
We'll see you in Discord.
We'll see you in Discord.
Yes.
All right. Okay, so for our third talk today, oh, my phone is ringing. Oh, it's my friend Scam Likely. I love Scam Likely.
I have Joshua. Mm-hmm. I think I know what they're calling about.
Yeah.
I bet your car's extended warranty is.
Oh, I bet that's the case. I should have picked up. Oh, darn it.
You should have. Now you're never going to get an extended warranty for your car.
I could have put them live on Bang Bang Con. Anyway.
Missed opportunity.
That's right. Anyway.
All right. Next talk.
So our next talk is Jonathan Kingsley, who is talking about ride on model railway signaling with Kubernetes. This is interesting. I use Kubernetes like vague. This is another thing I like know the surface of, and that is all.
We
so
were
I'm
trying
very
to
excited.
we were trying to categorize this talk as we were accepting talks. We kind of put them into categories, and we were like, how do you categorize this talk? Like eventually we just put it in the Kubernetes category. Like that was it. But it was the only talk in that category. So.
Yeah, that's right. It had like trip report. I don't know. Kubernetes. I don't know.
Trains,
like
but
hobby.
it's also, yeah.
Anyway, Jonathan is a software engineer at Orbit by day and a live production tech, pyrotechnician, and musical theater performer by night. His interests include hardware reverse engineering and information security, and he has once set a swimming pool on fire. Please welcome Jonathan.
Hello, everybody. It is absolutely marvelous to be presenting here the joys of ride-on model railway signaling using Kubernetes. I would, under any other circumstance, have a live demo in this particular slide deck for you, but unfortunately, I currently have a very blown-up boiler sitting in the background behind me and a not insignificant amount of copper piping, which I am currently in the process of reattaching to said boiler. But I do have a whole ton of very fun things to talk to you about when it comes to this. So let's kick this off very, very quickly. Who am I? Well, I am John. I do various snow sportsy things. I also do various train-related things as of the last half year or so. And I am well known for basically breaking things. In my off time, I am a professional blow things up-over, which I think kind of comes along with the whole corner of, for example, tiny steam locomotives. And I am a semi-professional buddy dad. I have to get him in here, otherwise he will never let me live this down. So model train signaling. So this is kind of an interesting topic because everyone, when you kind of say model trains and you kind of think about that, you usually think of, like, for example, like N gauge or like double O gauge, that corner of things. That is not quite what we're talking about today. We are talking about something a little bigger, as the ride-on section of the title may imply. We are talking specifically about trains in the 5 1/4 or 7.5 inch gauge variety. And these are of the size that you can kind of fairly feasibly build either in a small garden or anywhere else. A lot of conferences do tend to have tracks for these. Yes, that's my new favorite pun. Keeping an eye on the chat there. But these are some very interesting little bits of kit because they are probably one of the most accessible sizes that you can get for kind of model locomotives when you get outside of the kind of really model section. And this, for example, is one of my local model railway, and they, for example, have a whole bunch of various tracks that run around this little garden center that they have, and they have at least two or three different sections, of which the point is that they have a couple of different options in terms of how they route trains. And there's a ton of big, complicated things that you can do with train signaling. But one of the main concepts that you get is this idea of blocks. So this is applicable basically to all general methods of doing train signaling. In this instance, we're specifically applying it to models. So the way that this operates effectively is that you separate each section of your track into a block, and a block can have a single section of a train within it. The idea being that when a train goes into a block, that section of track is then effectively locked. There is no other trains should be able to go into that section of track until the train that has entered has subsequently left again. And the whole point of this is effectively to very simply avoid having trains decide to magically disappear into one another, as they occasionally tend to do if you don't control them. And one of the main ways that train signaling operates is using these little devices called axle counters. And like the name implies, they count the number of members of AC/DC that go through them as they pass by. The way that operates is that you have one of these at the entrance and exit to a section of track, and for every wheel and train axle that basically goes through it, it counts it. And then in order to figure out whether the line is clear, it will compare the number of axles going in and the time to determine the speed and if the train has cleared the area. It's a pretty simple concept. It's used in a combination with your like signaling control stuff, and which, by the way, I am going to be open sourcing a very fun signaling control, system in React a little bit later down the line once I have that fully together. Yes, it was in fact Guns N' Roses, not AC/DC. Completely slipped my mind there. But yeah, this is also coupled into safety interlocks. If you happen to have gates to cross the track, for example, that can be used to notify the driver. That's especially useful on the model scale, because you are invariably going to come across a situation where somebody is going to need to go across your very small track that you have definitely not laid directly across your front door, because that was the only like solid piece of concrete that you could find. And in that instance, you probably want to make sure that you don't run them over at the horrific speed of 4 miles an hour. So, how would you roll the hardware for this setup? Well, building your own axle counters isn't too hard. In my instance, I have been working on some 3D print files for them, run them up in resin, mainly because you don't want to do that type of stuff in anything that isn't UV resistant, because they're going to be outside the entire time. And you have a main kind of section of stuff, right? You have your on-train hardware, in order to handle your kind of general operation. You then have individual nodes that are split out across the network. So you've got your signals, you've got your points control if you're doing automatic point switching, you have your safety interlocks for things like your gates and sections where you're doing axle counting, for example. And we have a ton of these different nodes on this network, and they're all doing various discrete tasks. So looking at this from a software engineered perspective of things, took a look at this and immediately thought, let's put all of this on Raspberry Pis, because obviously. But secondly, the second solution here, well, the biggest question here is you have a whole ton of stuff across a very large section of land, and you're trying to get power to all of it. And the last thing that you want to do is to just kind of say screw it and electrify the rails, because that invariably tends to go very, very badly. So the solution to this is power over Ethernet. So you can, in fact, fairly easily, if you go for some of the newer AF specs, get PoE to run over very, very long distances. So once you have gone full steam ahead and networked all of your nodes together, you then have, like I say, the problem of how to deploy all of these individual pieces together. You have your on-train hardware, which is the bit that actually shows the driver how to whether stuff is in fact driving correctly. You have your hardware on the signals themselves. You have your axle counting. And you have your points in this specific instance. And each one of these I am deploying as its own discrete microservice. Because the great thing about microservices, among other things, is that you can deploy them on hardware as well as software. I actually kind of got the idea for this from, there's a really good article that I would highly suggest you go and look up, that is talking about, I think it's In-N-Out, one very large US fast food company that was actually using Kubernetes to do deployments to hardware in all of their kitchens. And basically push software updates to all of it almost on a like 4 times daily basis. So yeah, the solution is to run what's called micro Kubernetes. So this is a build of it specifically designed to run on Raspberry Pis and effectively allows you to go ahead and effectively route everything throughout. The flip side of it as well is that we then have to have some of the UI components, which is done through a combination of React and the worst JavaScript that God hath wrought upon the earth. But there's a reason that I'm open sourcing that later. It currently looks like somebody has someone's run a train through it, actually, unsurprisingly. And finally, at the end of all of this, in the joyous fun that we get off the back of it, is this giant horrific hellscape of a network where we have effectively a console-backed service discovery system running on a train, which then learns every single attached piece of infrastructure, picks up all of the associated nodes, and then communicates with the wider network using a local LoRa network. If anyone is familiar with that, that is a very nice little low-power Internet of Things network system that you can use. So, right, finally, why does this all matter? Well, safety systems are incredibly important because occasionally you will get situations where your trains will magically forget that they are in fact supposed to be more than 8-bit and have more than 256 axles on a train, and then magically your train will disappear. You do not want this to happen, especially if it happens to be in your garden. Thank you very much. I have just barely hit time on this. I'm frankly not quite impressed that I managed to at all. If you would like to find out more about all of the fun Steam Train and non-Steam Train related things I'm doing, you can find me on Twitter. I also stream on Twitch under the same name, and I am currently working on a desktop flamethrower. So if you want to know more, please do come along and say hi. Thank you very much, and stay safe out there.
Ah, fantastic. Hey, were you watching the Discord?
Oh my gosh, the pun! Everybody was dropping puns. I love the the very last one was. I'm a little disappointed that that wasn't written in Ruby on Rails.
Oh, that's pretty good.
Oh my gosh. I'm sorry I stole your
good.
pun, Aaron. Thank you for submitting that to Discord so that we could all enjoy it.
Ooh. Oh, that's pretty good. And the amazing thing is that John was continually like I can't read Discord while talking, but like he clearly could like pick the puns up periodically.
Yeah,
very good. Anyway, I think it is time for our last and final session speaker of Bang Bang Con, and of course we have our keynote coming after this. But coming up next is Martin Gaston, who is going to be telling us about making our own Napster so we can party like it's 1999. Winamp. Between frequent conversations about the magic of the 90s, Martin works as a software consultant at 8th Light. He likes fiddling around with fussy protocols, wants everyone to feel like they can pursue a career in tech, and is absolute. I'm not going to read that. Martin is great at writing a personal bio. I disagree.
Great job, Martin.
All right. In any event, please welcome Martin to tell us about Napster.
Hi, everyone. It's so intimidating to follow so many great talks. And I'm kind of just composing myself after those 3 amazing talks. But yes, hello. I am proud to admit that the first MP3 I ever downloaded was Ricky Martin's 1999 pop banger, Livin' La Vida Loca, which I would then play dozens of times a day on an outstanding program called Winamp. And I downloaded this hit from the MP3 file sharing service Napster. And if you miss Napster, it introduced peer-to-peer networks to the world. It felt edgy and anti-establishment, and despite what the music industry was saying at the time, it was so obviously like staring at a portal into the future. And recently, I've been trying to recreate my own Napster. It's been a really fun journey, and it's taken me into internet sockets, numerous servers, and eventually playing an MP3. And today I'm really excited to share that with you. And I'll start at the beginning via a pretty amazing reference from a reverse engineered Napster called OpenNap. So if we imagine we're in 1999 and we just booted up our Napster client on our Windows 98 machine, the application would call a redirector server, which was like a load balancer. And this would point you to a nearby server that hopefully wasn't overloaded. You'll then connect directly to that server. And we won't worry about the redirector anymore, but all of these connections, whether that is to the redirector, to your main Napster servers, or even to another client, which is known as a peer, these are all handled by sockets, which are provided to us by our operating systems. And you probably have a bunch of socket connections going right now, with at least one being used to watch this talk. Sockets basically power the whole of the internet. And if you have netstat installed, you can run that command now to take a peep at what you've got on your machine. Now, much of this incredible socket API is written in C, but almost all languages have an abstraction of it as part of their standard library. We'll be using Python today, but if you've never used Python, please don't worry. Hopefully, a lot of the syntax will be pretty familiar-ish if you've used another dynamic language like Ruby or JavaScript. So if we quickly dive into some code, we can load up our socket library. We can declare a variable to represent an internet socket. Now, there are other types, but the internet is what we're after today. And we'll also strictly be communicating with the TCP protocol. Again, there are other types, but this one creates a reliable two-way connection. Now, with those, we can create a socket. And before we jump into Napster, we'll start with an example using HTTP by firing some binary data to the Bang Bang Con server. And we can even add a couple of headers to make it look especially legitimate. And we can get a really cool response back. And this turns out to be a nifty piece of HTML telling us to use HTTPS. Now look, this is all really cool. We're using the sockets API and TCP and all of this stuff, and we're not really worrying about it at all. The operating system is doing most of the work here. What we've done is taken some data and wrapped it with some HTTP protocol headers, and which in turn gets wrapped in some TCP headers by our socket library, and then some IP data gets added. Again, none of this is being done actively by us. And then some hardware data gets wrapped around a lot of it, like your Ethernet port or your Wi-Fi connection. This gets popped on at the end. And now when we whiz this packet of data down the magical internet pipes, and the Bang Bang Con server picks it up and does the same in reverse, stripping off headers until we're down to the original data that we sent. This layered network model means that we can focus on our application. And it also means I can give this talk without having to understand about 1,500 pages of network programming. And so when it comes to our Napster server, we're still using IP and sockets and TCP. All of those parts are the exact same. But while bangbangcon.com knew how to speak in HTTP, we need to make a server and a client that can speak in Napster. Now, actually setting up the socket infrastructure is very similar in both. For the client, we once again create a socket. We connect to the IP and port of a Napster server. We send a special Napster data packet, and then we read the response from the server, and we're done. Now, we'd need to code a little more to keep our connection alive, but this handles a single send and receive flow. And over on the server side, we start by booting it up with Python's socket server library, which is another abstraction on top of socket, and it will sit and wait for connections. We can set up a handler for when a client connects. We can grab our socket. We can receive data from the client. We can process it however we see fit. And then we can return a response. Now, There's a lot more we would need to do in a big production system with thousands of active users, but this is already quite a potent client-server connection as it is. And we can now start to think about what the actual data we're supposed to send between the client and the server would need to look like. All messages in Napster take the form of a packet that can be divided up into length, type, and data sections, with length and type being 2 bytes each. The value of length is the size of the data section in bytes. So our Napster client and server know how many bytes to read from the socket. Now, the ones and zeros of binary aren't something we really have to think about today, but I did do a talk last year about reading files from a PlayStation memory card, which goes into it in a lot more detail if you'd like to know more. What we do need to know is that we can encode these ones and zeros into human readable characters using a mapping called ASCII. We'll use this in the data portion of our Napster packets. We will also need to know that we write our length and type bytes, which are, remember, 2 bytes each, in hexadecimal format, which is like counting from 0 to 15, only we can do that with 1 digit, as we have 6 more digits added from A to F. It's a little bit sort of a mind-bendy thing. But the 0x part is just a way of making all the hexadecimaliness a bit more explicit. With this in hand, we can start to assemble our Napster messages. There's about 130 odd in Napster, but we'll only really be using a handful today. These 3, logging in, registering files, and searching for files, are the core ones for now. We use the length, type, and data sections of our message to create tiny little agreements between the client and server in how to communicate with one another. And the next step is gluing together our connection and our protocol and actually downloading an MP3. So Napster is centralized, which essentially means it takes on the role of a big MP3 librarian. And when we connect to our Napster server, we register a list of all of the MP3 files on our hard drive, which the server plops a record of into that index server. Details on the specific implementation are hazy, but I would imagine it was probably a big database. And so when a user runs a search for a certain file, the Napster server queries the index server to see if there are any matches. And if there are, it returns a big list of all the users it found. And inside this list will be the details needed to connect to the user who had the file that you wanted, allowing you to then initiate a direct transfer with them. And then finally, to get the file you were after. So actually implementing this is once again a very similar pattern to what we've already seen a couple of times now, an internet socket using TCP. We set up a little data class that would have the file name, IP of the server with the file, and the port. And we set up a little acknowledge function, which reads a single byte and returns a Boolean as to whether it was a string of 1, which we'll use in just a second. Then we set up a socket again. We connect to the peer who has the file we want to download. We acknowledge that the first byte we receive is that one, which is like our little secret message. Then we ask for the file name that we want, and then we download it in nice little 1024 byte chunks. Meanwhile, the user we're trying to download the file from has got their own little TCP server running as well. And in their handler that fires when a user connects, they get a socket, they send a single byte of 1, they receive the file name from the user, and if they have the file, they send it in nice 1024 byte chunks. And again, we haven't really written too much code today. And while this certainly isn't production ready, these are the same fundamental blocks for a sort of genuine Napster server. And so I think we should run it. And this is the bit I'm super nervous about, because while I'm pretty sure I set my sound up and I don't want to spoil what's coming, I just hope I've set my sound up. So to see it in action, I deployed my server to AWS. I set up a client with a shared MP3 on another computer, and I can show you the client running from my computer. Ricky Martin is copyright, of course, so I didn't want to tempt fate here. Instead, I'm looking to download the distinctive and iconic MP3 that came with all Winamp installs, the powerful Llama Whippin' intro. And after downloading it, I can add the file to Winamp and I can click play. And those 5 seconds are kind of my payoff for watching the rest of this talk. If you used Winamp back in the day, hearing that is probably a concentrated blast of nostalgia. If you did not, that was probably a very confusing 5 seconds. But with that, we created our own little version of Napster. Networking is such a fun and broad topic, and while we only really scratched the surface today, it's been so exciting for me to work on this and to have the opportunity to share it with you. Hopefully it's piqued your own interest a little bit into the sockets and protocols that underpin so much of our day-to-day lives. I have the code and some resources for more information for anyone who is interested on my GitHub, and please feel free to drop me a message on Twitter if you'd like to talk about this some more. And I would just very quickly like to end by saying a special thank you for all of the amazing organizers for putting together this wonderful conference, which always feels like such an inviting and comfortable space to be in. Thank you.
Thank you. You are muted, Joshua, and I can hear myself. So I don't know what you've done, but it's very exciting.
Winamp. It really whips the llama's ass.
Is that what we're supposed to play during the end of Martin's talk? Okay. I mentioned in chat. We'll edit that in during post. So
I hoped that you could hear both me and welcome to Linux audio.
yeah.
Anyway, okay, so that concludes our session talks for today. And if you missed one of our amazing 4 session talks, you could watch the sync watch later today. And I was so clever to put it in the script that you could watch the sync watch later that I forgot to look up when the sync watch is.
Oh, the sync watch.
Anyway,
I don't know.
Thank you so much to Laura Kurup, to Kimmy Wilbur, to Jonathan Kingsley, and to Martin Gaston for their fantastic talks today. If you liked them, you should tweet at BangBangCon, hashtag #VirtualBangBangCon. Okay, so after we're about to have a fantastic keynote. I'm going to let Erdi introduce our fantastic keynote. But before we do, we're going to go on a 5-minute bio break. This is the plan here. And so we are about to have a countdown on the screen again. And I'm going to go make breakfast. And you can all do other bio break related things. And then we will be back in 5 minutes. Cindy, roll the tape, please.
Did you manage to make breakfast in 5 minutes? Wow, look at that.
I Cindy could probably see it because it says that only the host can see you when you're not. But like I ran, like I was in the kitchen and I just came running back over to my terminal. I saw the countdown. And I was like,
I want to just do one little piece of banter, just because it's exciting before we introduce Kate, which is that our Business Insider article came out, and it focuses mostly. So I mentioned the other day that we got interviewed for Business Insider, myself and Julia Evans and Lindsay Cooper. All got interviewed for Business Insider. The reporter was super nice, and we ended up getting an article published yesterday. It mostly focuses on kind of our I'm not going to say conflict because there's no conflict, but our name overlap with BTS and the kind of the collision. That's a meta word for it. The collision between our kind of namespaces in the real world. And so it's super cool. Someone can drop a link maybe in Discord. I also mentioned though that we don't really nobody's really written any articles about us. We don't really have any media presence. If anyone knows any reporters, send them our way. We would love to talk to people about Bang Bang Con and let more people know about what we do, and maybe in time for next year's conferences, which I'll talk a little bit about after Kate's talk. So I won't delay anymore. I just wanted to fit that in there somewhere. Yes, let's introduce Kate. All right. So everybody, please welcome Kate Temkin. Kate Temkin is a hardware hacker and low-level engineer who spends most of her time exploring the hardware-software boundary and figuring out how to empower people with educational technology. Her recent interests include building hardware, software, and gateware for USB development, reverse engineering, and hacking. When not hacking hardware, she maintains a variety of open-source projects, including Luna, ViewSB, FaceDancer, and Great FET, and probably spends more time than she should reverse engineering and creating educational materials. Take it away, Kate.
All right, hello. Hope everyone's doing well. It's a lot of good talks this morning. This is, I think, the first time I've ever done a keynote that immediately followed a 5-minute countdown timer. So I'm pretty excited to kind of take that energy into this. I have about a half hour of material, which is relatively challenging for me because I have a tendency to talk pretty much continuously, so I'm going to get started. But this talk is all about a specific project that I've done lately that I thought was something that was fun in a sense that is, it was done specifically for the purpose of solving a problem that had kind of gotten stuck with me. So, get this. Gotta get the mouse in the right window for this. So, who am I? I am Kate Temkin. I lead the more digital side of a company called Great Scott Gadgets. I do a lot of things that are designed to empower people with technology. Kind of one of my main goals is to take things that people don't easily have the ability to touch or see or kind of interact with, things like USB or things that are going over wireless protocols, and make those things that you can actually interact with, because in interacting with them, they start to become the kind of things that you can play with, and playing with them, you can understand them. So kind of my whole thing here is that every little bit of computing that we do, I think, should have a human focus at the end of it. I love doing things that directly empower people, that allow people to understand things they wouldn't, or that enable people to do things they wouldn't have been able to do, either because of the price of technology or because of some technical limitation. And so today I'm going to spend the next half hour telling you a story about a particular set of circumstances that led me from this kind of concept of deriving joy from, let me see if I can use a laser pointer on this. Maybe not. Okay. So the particular example of deriving joy first from non-forbidden computing, and then this kind of journey in order to actually build a project that allowed us to extract some joy from what I'll call forbidden computing. And to understand this, I'm going to tell you a little bit of backstory. I have a particular good friend who is extremely, extremely passionate about taking her entire setup with her. One of the things she loves to be able to do is to be able to go out into the middle of nowhere with nothing other than the phone she has, and then be able to use that phone to do pretty much any computing task. And one of the things that enabled this for a very, very long time is a program called UTM, which allows you to run virtual machines on iOS and Apple devices in general. And that program was amazing because if you wanted to run something that was a Windows application or a Linux application, you could boot up a virtual machine and relatively quickly be able to access everything like you would on a full computer. So you don't have to kind of lug around a laptop. You don't have to lug around, an iPad, anything like that. You can actually do a lot of your computing directly from the palm of your hand, not remoting, just using these virtual machines. And that was a really cool technology that, in this case, sparked a lot of joy. But unfortunately, eventually, Apple updated their operating systems, iOS and iPadOS and those kind of things, in order to block the technique that was used for allowing these virtual machines to run. So we reached a point where you had a choice between either keeping a low version of iOS and not getting the newest features and security stuff, or being able to continue or being able to get those updates and not be able to use UTM. So before we get into the actual story of how we overcame those limitations, first, let's look at how this happened. How do we wind up in this situation? And in order to do that, you have to understand the backend that actually drives UTM, which is a piece of software called QEMU. And this slide, even though it's packed with text, is actually just a screenshot of the QEMU website. The most important thing is that QEMU is a piece of emulation technology that can be used for a variety of things. You may be familiar with QEMU as a virtualization front end, where it does things like emulate disks and allows you to run hypervisors like KVM or Zen. But I'm actually interested in what I think is kind of a cooler use of QEMU from my perspective, which is full system emulation, where QEMU actually emulates the entirety of a computer. And the really cool thing about that is that the computer that you're emulating does not actually need to be the same architecture as the machine you're running. So you can go and emulate a Raspberry Pi on your x86 machine, or you can emulate an x86 machine on your iPhone, which is an ARM64 processor. So this is really, really neat, especially if you want to be able to run something like full Windows on your phone. What's really cool here is the way this works. The core of QEMU used this way is an engine called TCG, which is the Tiny Code Generator. And the Tiny Code Generator is a kind of core computational translation engine that does binary translation from whatever your input is to whatever your output format is. So in this case, in the example I have on the slide, it will take x86-64 machine code and then allow you to run it on an ARM64, an ARM 64-bit processor, as we would if we were running this on an iPhone. So if we take a look at the input of some example x86-64 code, we can see the very first thing that happens is the block of computing that you want to do, represented as a bunch of machine instructions, wind up getting converted from their original representation into something called an intermediate representation. And this IR, intermediate representation, is very similar to the IR that exists in compilers like LLVM. It goes from the actual things that the operations are doing to the individual kind of core abstract ideas of computation. So it's trying to break everything down to a more abstract level. So if you look on this slide, the first instruction that we had in x86 was taking register 8, XORing it with itself, which happens to translate to the intermediate representation kind of abstraction that says really what this is doing is it's taking register 8 and moving 0 into it as a 64-bit number. As we go through here, every one of the operations that was represented in x86 code gets translated to this intermediary format. And that intermediary format now has absolutely no relation to the initial platform, the initial lab platform that we're emulating. Instead, it's kind of a generic way of encapsulating the behavior we want. From there, our system actually takes that intermediate representation and compiles it into an equivalent set of opcodes for the target architecture. And this process is a little bit lossy. As we go through this, we generally tend to get less efficient code out of this machine than we did coming in, but it's still code that can be run natively on your target architecture. And once you've done that translation, once you've done that binary translation, you can actually take this block of code and run it every time you would be running the equivalent x86 code. So you don't have to go and do new processing. You have native code that can run, that can do all the same things as your x86 code would have. So the whole magic that enables QEMU to work in ways that allow you to run x86 programs on your AR64 phone is just-in-time generation, where the whole computer, your whole representation of your emulated computer, all the execution that goes through that winds up being translated into native code, and then that native code is allowed to just run. And then once it's been translated, it just kind of stays there in a cache and can just be run over and over again without having to rerun this whole process every time we want to run that code. And this actually can be pretty darn performant. On a VM that takes about 12 seconds to boot natively, this QEMU engine can actually get that to boot in about 18 seconds using just-in-time generation. And that's not a comprehensive benchmark, but it gives you a good idea of the kind of overhead involved in those translations, which is pretty minimal. Okay, so what about using this on your phone? If you have a modern phone, you have the slight problem that all of the code that you're able to run on that phone is usually required to be signed by a developer. And on Apple phones, every bit of code that runs should be signed by the person who actually authored it, which means that if you're generating your code just in time, if you're generating that code at the last minute in order to be able to run it as part of that QEMU process, as part of TCG, you're going to run into an issue because Apple has put protections in place preventing you from being able to have memory that you can both fill with instructions and then execute from. No memory can be both writable and executable unless you have a special entitlement that Apple doesn't give to general application developers. So essentially, if you go and try to do this on modern iOS, your just-in-time compilation or just-in-time translation is actually forbidden. So we have gotten fully into the domain of forbidden computing. Now, one obvious workaround for, I guess I shouldn't say obvious, one workaround that's obvious if you're really deep into this problem space is that you can run the whole virtual machine. You can run the processor on another virtual machine. This virtual machine being one that is a virtual machine in the type of a language VM. So we can actually take this and use it like, if you think about this as like running code on a Java virtual machine, this is very similar. There's actually an interpreter that takes all of the intermediate representation, all of the stuff that you get from that kind of QEMU processor agnostic format and just runs it. It has a set of virtual registers, and it knows how to, it knows when it sees the intermediate representation for move 0 into register 8, it's capable of running some code that does that. Problem with that is that this is a big machine that is running in C that has these big jump tables and has all of these indirections to access a set of virtual registers. So you're actually running a emulation of a machine on your phone that then in turn runs the emulation of the machine. This level of indirection makes everything kind of get a little bit unbearable. Let me see if I can start this video properly. So this is booting ReactOS on this interpreter running on UTM on an iPhone. And one thing you might notice is that as I'm sitting here and talking, the whole system is very gradually loading things. If you run the that same reference piece of VM that I had that booted in 12 seconds native and about 18 seconds on the just-in-time runtime, on the interpreter, it took something like 90 to 120 seconds just to be able to boot up. So everything gets really unusably slow. Really, if we want this to work, we're looking for something that is ideally not painful to use, still fun to use. And that means maybe somewhere between that 18 seconds and maybe 40 or 50 seconds to boot, not something in the hundreds of seconds. So we're left in this problem space. I have this friend who has been loving running these virtual machines on her phone, but suddenly can no longer do that in the typical way because we can't run generated code. We are limited by Apple to only being able to run code that comes pre-made and that we're able to sign at the time that we're going to put that code on a phone. So this is the kind of problem space that got me thinking. So in the process of her kind of explaining that she was super bummed to lose this, we started talking a little bit about different ways around this, different ways that we potentially could start running things. And we tried running out the interpreter, and it was just too slow to be used. But there is this one kind of saving grace in all of this, which is that we can actually still run code as long as it's been pre-made, as long as it's been pre-generated. And you start thinking, well, okay, if we can run pre-made code, what if we were able to pre-generate every bit of code we might need? Now that sounds like a lot because theoretically there are infinite programs you could stick into this if you have infinite space, right? There's infinite solution space for all of these things, and to be able to capture every possible program and pre-generate code for it is impossible. But what we can do is we can take a look at the various pieces of intermediate representation that QEMU is capable of producing. So if we have an instruction like move a value from R0 to R1, or in this case from R1 to R0, we actually have a piece of AR64 code, in this case ARM 64-bit code, that does that. And so we know how to generate a single little bit of pre-made code that handles that particular case. If we were able to generate possibly a whole variety of these little tiny bits of code, these little things that we'll call gadgets, we could potentially write whole programs that way, right? But something still needs to come and stitch all of these things together, right? So if we had a pool of all of these, it would be really nice to have the ability to go and kind of thread together all the individual pieces that we have. One technique for doing that is to come up with a big list of every single gadget that corresponds to a potential thing that we might want to do. So if our program was moving X1 into X0, register 1 into register 0, and then adding register 2 and register 1, storing that result in register 0, we can find gadgets to do that, and then stitch those together by adding a little bit of code after each gadget that goes and moves its way to the next one. So we moved from a model where we were just stitching together machine code instructions to a model where we take a list that has all the different potential gadgets that we want, just kind of sitting there address after address. And then we write some code that says, let me go into this list, grab the next address, and then just jump to it. So we actually can have it so that every instruction that we want to run is followed by a really simple little epilogue that moves to the next instruction. And at this point, what we're actually doing instead of running code that we've generated is taking a whole bunch of pre-generated code and threading it together. So we need every possible gadget that you might run into for this to work. And this is very possible if you have something like 16 registers on your system, because you can go and generate add R0, R1, R2, add R0, R1, R3. You can go and actually generate code that generates every single one of these little gadgets. And so what I did is write a Python script that goes and generates the low-level assembly for every single one of the instructions that I use to implement all of the QEMU intermediate representation instructions. So here we have a whole, just a little snippet of something that is saying, okay, for example, midway through the slide, we have load a 8-bit unsigned value. And then I have a little bit of ARM code that has some placeholders. And this Python just goes through and substitutes the actual values for each individual possible argument into that template. And what we wind up with is a whole bunch of, in this case, inline assembly that implements every single possible operation in QEMU IR in AR64 code, pre-generated, all in big files that we can go and sign these and then be able to operate that kind of stitching together technique on all of these little pieces. So this kind of transitions the way that we were working on this from something that took machine code in and produced machine code out into something that took machine code in and outputs these chains of gadgets, which are then threaded together. This new technique I've chosen to call the tiny code threaded interpreter, because instead of the regular interpreter, which went and actually took that intermediate representation and ran it manually, we're actually taking pieces of machine code and stitching them together, scheduling where all the jumps go, so that we can actually have a continuous stream of executing instructions. So this required one last little piece, which is to implement that the actual piece that transforms from intermediate representation to those chains of gadgets, which it turns out is actually just a big collection of these opcode emission instructions, where instead of saying, let me generate the machine code for a bswap instruction, we're actually saying, let me generate a pointer, a gadget pointer in this case, let me add the address of the code that already exists that performs this operation. And what we get out is something where the intermediate representation is translated not directly to machine code, but to a collection of gadgets that then run on this new weird kind of machine that we've made, which is really a subset, a specialized subset of our ARM processor. And so what we're able to do is, just like before, we take the intermediate representation and produce something that can be run natively on our processor. And that essentially means that we're going to be outputting these long chains of gadgets, which in turn do all the same operations that we would be doing on that target processor, but with just little bits of extra code stitching everything together. So what we have is a really cool way of creating a system that is capable of running native code, just like the original was, that doesn't have to interpret things every time, but which is doing so using these generated pieces of code, which were then which we're capable of signing at the time that we build QEMU. So all of this put together, we can finally go and actually check to see how the performance is. So what I have here is a comparison of TCI on the left, which is the basic interpreter, and on the right, TCTI, the threaded interpreter. And we can actually see how quickly these two comparatively boot. Now you can mostly ignore when the windows change size, because that is me tapping on the screen during these recorded videos. But if you look at their content, what you will notice is that TCTI, while not the fastest thing in the world, is significantly faster than TCI, which is still figuring out how to run the desktop and do the basic rendering at the time that TCTI has been long done. And so by making a more efficient interpreter, by using this kind of cheating technique, we're able to get ourselves to something that is usable in a reasonable amount of time. So we've gone from something that was completely computationally forbidden to something that is now actually usable. And this eventually made its way into UTM, the original application at the start of this. So we've gone from something where we had a restricted computing environment where we weren't allowed to do anything just-in-time translation-like, to something where we, within those same restrictions, now have a even weirder way of doing things that still circumvents the restrictions. And on using this, we're able to run applications again and virtual machines again on Apple devices. So just to give you some statistics, I am going to preface this by saying my goal in this was not to measure performance. These are not scientific measurements. I specifically did all of this for the purpose of being able to do something that was fun and for me to implement, something that sparked joy for my friend who would no longer have to be without those virtual machines, and something that was going to satisfy the itch I had while thinking about the problem space to actually prove that this technique works. So in our limited empirical testing, which is booting that same reference image, what we actually find is that a TCTI boot of that reference image takes about 36 seconds. So in its best, in the best case of all of the trials I did, TCI, the regular interpreter, the non-hacky interpreter, was only able to make it to, I believe, like 78 seconds in its absolute most optimized form. So we basically cut the boot time in half just by doing our computational stuff in a little bit of a different way. And so this is awesome because I think this is a really great example of something where you can take a really simple problem, kind of apply that human factor, and translate it into the real thing, the real kind of outcome that I would hope to get from computing, which is that we can use this then to spark joy. And so at the end of the day, we learn a kind of extremely powerful lesson here, which is, I put pithily as, when life forbids you from computing, spark joy with a newer, weirder computer. But I think with a little bit of that pith removed, the real thing that I would love for everyone to take away from this and take away from all the rest of the talks at this kind of amazing gear of various neat technological excitement is that when, at the end of the day, what you really should be doing as you build technology is thinking about ways that your work is going to make things better for people, right? The whole goal here is to focus on that human factor. And I hope this story is something that shows you just a really simple run through of my thought process when a friend of mine was feeling down because of a computational problem. So that all said, I would love to go and answer some questions from Discord, which I have to catch up on. So, yeah, just checking in on comments as I go. Yeah, so the things I'm seeing in the past there, like, I honestly think this graph here, the pithy joyous bar graph, is something that every one of your technical projects should have somewhere in your head, so that you can at least kind of answer the question of what is this doing for me? All right, I am now yeah, we can go to a panel. Sounds good to me. Answering organizer questions here. The question from Discord is, am I going to name the debugger for this Inspector gadget because it's a rad name? There actually is a built-in debugger for this that is nameless. So if you want to go into the code base and PR that, you are completely welcome to. All right, so hopefully we're going to get some talking heads in here.
Hello.
How's it goes?
Oh, that was amazing. Oh, I'm so excited.
Yeah, please go ahead. Yeah, please.
A question we got in Discord is how this technique handles immediate values, and those are either there's one of two ways to handle that. One of them is if they're very common immediate, we build a gadget that has that immediate hard-coded. Otherwise, we put the immediate right in the instruction stream, just like you would any other machine code. So that means that what you actually wind up with is a gadget pointer, an immediate, and then a gadget pointer, and it's up to the gadget itself to go and pull that value out of that instruction stream in much the same way that a processor would do that itself in instruction decoding.
I was gonna ask. I was gonna ask about like cache characteristics and this and that and the other thing, but the actual question that I really have is, did it work? Is your friend now able to take her iPhone and do stuff like into the woods and like do stuff with it?
Yep, it's actually now fast enough to be able to be used. I'm getting blurry for some reason, but it's okay. So it's actually fast enough to be usable in. It's not as fast as it would have been otherwise, but it's definitely usable, and it has made its way into the core of that original program, UTM. So now everyone who's in this situation can do the same thing, which is kind of awesome.
That's very exciting.
They named it the very flattering UTM Slow Edition.
I'm very curious about like many parts of this. I'm not sure that like I could pick your brain on this all day, but it's not immediately clear to me that I will have all of the Bang Bang Con attendees listen to me ask question after question after question after question about like cache performance and like, wait, you could do JIT before iOS 14.4? Like, so how did that work? And all that sort of stuff. So I think we should send that over in the Discordly direction. And thank you, Kate. Thank you for, the thing that I liked about this was not just that it's a really cool hack, but it's important to do things for people. And I think that's the at the very beginning, you had mentioned that you can understand the world by playing with it. And this is kind of how I feel. Like here I am in my lab setup here. I have an idea for a Bang Bang Con talk next year that is exactly that, like figuring out how. Wait, I'm not going to say it out loud. The other organizers will hear it.
I won't listen.
But all the same. But by playing with objects, either physical objects or software objects, you can understand how they work, and kind of just build your mental model. I don't know. I really like that. That's my aesthetic.
That interactivity is something that things never feel real for people until they can get their hands on them. So being able to make things tactile is such a powerful thing in computing.
I agree. Thank you very much, Kate.
Right.
Thank you for helping us close out Bang Bang Con this year.
Oh, it was awesome. Thank you so much for putting on an amazing virtual conference. Really glad to see these things kind of thriving even when we're all socially distanced. So it's been great.
All right.
Great.
Cindy, will you? Yes. And let's get all of our organizers up here on stage.
Oh, it's going to get crowded.
Oh, probably.
Excellent.
Hey, everyone.
And Dev is somewhere.
He's with us in spirit.
He's with us in spirit. This is our organizing team. I just wanted to get us all up here. I think we actually said that we were going to do this after my little final talk, but I figured you could all say hi anyway. And so I would like to... Cindy, can we put... I'm sharing my screen. Can you put that up next to all of us? Beautiful. Oh, I shouldn't have gone with that background. It's a little bit of a clash. All right. All right. Well, thank you all so much for coming to Bang Bang Con 2021. This year ran so smoothly. I think we finally figured out this whole virtual conference thing just in time for us to hopefully go back to in-person conferences next year. No announcements yet. Hopefully we will have both Bang Bang Con West and Bang Bang Con flavored Bang Bang Cons in 2022. But either way, thank you all, so much for bearing with us as we've transitioned to this virtual format. It is so energizing and inspiring to see all of the work of the people who have contributed to Bang Bang Con this year. We'd like to give an extra special thank you to Cindy with Confreaks, who did all of our AV checks, who did all of our live streaming, who did all of our editing, including turning our live streams around fast enough to go up as YouTube premieres for our sync watches, sometimes in as little as 6 hours. And that's just amazing, and just so much work. She's really carried this conference across the finish line, and we are so incredibly grateful to have her on our team this year and of course so many years in the past. If anyone is running a conference, we enthusiastically recommend that you hire her. We are happy to put you in touch. Or she has a website. Also, thank you to our captioners, Mirabai, Joshua, Amanda, and Lydia. Bang Bang Con is always a workout for them due to our very fast speakers, but of course they all did amazing. Thank you all. Please drop a huge round of clapping emoji in the general channel on Discord for all of our speakers who shared their knowledge with us and their enthusiasm and their excitement and their joy this weekend. Thank you all. Obviously, Bang Bang Con is not possible without you. Thank you also to our sponsors and donors who made this event possible. I want to point out that for the most part, it's people like you who are watching who convince your companies to give us money. Please keep doing that. It is because of your work and your funding that we're able to have such a well-run stream with captioning and pay what you want tickets. And hopefully next year we'll have catering again. So I'd like to I'd like to turn it over to Lindsay, who will talk about our organizing team.
All right. Hey, everyone. So I'm Lindsay Cooper. I'm one of the Bang Bang Con 2021 organizers, and I am a co-founder of Bang Bang Con and our West Coast edition, Bang Bang Con West. And I've been working mostly behind the scenes this year to help make this all happen, but I want to say something about that behind the scenes work that our whole team has been doing this year and that we do every year. So I'm going to try to take everyone in order here. So first, Joshua. Where do I even begin? So Joshua was part of the Bang Bang Con West team when we got started. He's now part of the Bang Bang Con organizing team. He's also serving as the president of the Exclamation Foundation board this year, the nonprofit foundation that oversees everything that we do. And one of the things that Joshua did behind the scenes this year that was, I think, especially important was that he helped spearhead the overhaul of our code of conduct. So as he talked about at the beginning of the conference, we really wanted to move to having this code of conduct that really captured what we were about. And it was largely because of Joshua, who had wanted to make that happen for years. So I wanted to personally thank him publicly for making that happen. As if that wasn't enough, Joshua was also involved in helping make it rain on us with sponsor money. He was part of talk proposal reviewing, and he's been doing a whole lot of emceeing of talks. So thank you, Joshua, for everything that you're doing. Erdi, again, where do I even start? So Erdi is also a member of the Exclamation Foundation board. He's serving as secretary of the board this year. He also reviewed all the talk proposals. And I might add also that our talk proposal infrastructure, the tools that we have for reviewing talk proposals were all built by Erdi. So we have several tools for that because we have a lot of talk proposals to review, and it would be hard to do without tooling. So he makes that all possible. And he's also a fantastic MC. So we're incredibly grateful for all of that. Julia, oh my gosh. So Julia, talk about making it rain. All Julia has to do is tweet and people start throwing money at us. It's absolutely incredible. So thank you, Julia, for helping make all these wonderful sponsorships happen. Julia was also in charge of all of our t-shirt infrastructure this year. So our store, where hopefully a lot of you have gotten your cool t-shirts and sweatshirts, Julia set that up. She also reviewed all the talk proposals, and she also helped spearhead the code of conduct overhaul along with Joshua. Alicia was also heading up talk proposal reviewing. She did a lot of emceeing, and she did all this on top of giving a talk that was more than just a talk. So that was incredible. But perhaps most importantly, Alicia was part of our incredible two-person speaker hospitality team. So together with Sarah, Alicia was the person who interacted with all our speakers, helped make sure that they had everything that they needed, and guided them through every step of the process of being part of this conference. And this task of speaker hospitality is something that's really been important to me since the beginning of Bang Bang Con, because I know, keeping the speakers happy and making sure that they have what they need is so important to making sure that the talks are good. And so it's because of our incredible speaker hospitality team that this is even possible. So thank you to Alicia. And to do all this on top of also giving her own talk is just even more heroic. So absolutely incredible. Sarah, talk about heroism. So not only was Sarah the other half of our incredible speaker hospitality team, not only did she review talk proposals, not only has she been doing a ton of emceeing, but she was also the one who did the last minute heroic JavaScript hacking on our website that made our talk picker work, or our live stream picker work. And just not only that, but I should say, Sarah is the newest member of the team, but she leapt right in to our frankly rather eldritch website code and made everything work and modernized everything. So thanks to Sarah for joining this team and becoming a very integral member of the team incredibly quickly. We could not have pulled off this conference without Sarah. And finally, Dev is not on screen right now, but I want to talk about Dev. Dev is a co-organizer of Bang Bang Con West, who joined the Bang Bang Con team this year. It really is touching to me that Bang Bang Con West people are now coming over to the Bang Bang Con team. He also reviewed all of the talk proposals, and he did all this while being a grad student, and trying to wrangle a lot of responsibilities. So I'm incredibly thankful to him for being part of all this as well. So I'm in awe of every single one of you and all the incredible hard work that all these people do to make this happen in their free time. So I'm still involved in organizing all this. So for instance, this year, I'm serving on the Exclamation Foundation board. I reviewed talk proposals, I've been doing some live tweeting, and I even talked to the press about how we are not BTS. But I am actually very proud of the fact that I could walk away from Bang Bang Con and all of this would keep working without my involvement. And it would in fact be much better than it was when we started in 2014. And I want to mention just two other people, the two other members of the Exclamation Foundation board, Maggie Joe, our treasurer, and Gina Lee, our assistant treasurer, who are doing the incredibly important work of managing our foundation's finances so that we can actually pay all of our speakers and all of our incredible streaming team and our captioning team. So thanks to them for the wonderful behind the scenes work that they're doing. And with that, I'll turn it back over to Ernie.
I'm muted. I wasn't. All right. Yeah. So, gosh, I thank you, Lindsay. First of all. Yeah. So, I guess I want to talk a little bit about how Bang Bang Con almost didn't happen this year. For a moment there, when we were getting, we were just kind of starting to rev up the organizing team, and we were like, gosh, maybe we should just cancel this year. Like, do people really, really need another 2-day sit at your desk weekend staring at the computer? That's what a lot of us do for our day jobs, and so that we were all just like exhausted thinking about it, and I think it was me even who just proposed the idea of giving up and trying again in 22. And I am so happy that you all did not listen to me. I mean, I'm as many of you are, like, I'm exhausted. I have an amazing but tiring 2-year-old daughter. I have a day job. My living situation is desperately in need of cleaning. I have not really programmed for fun since the pandemic started over a year ago, and I was like entering this week, which was a lot of work for all of us, just exhausted, and I was worried that it was going to burn me out even more, and instead I feel so revitalized. Gosh, after Rocky Kev's Net Monster talk on Tuesday, I spun up glitch.com and like tried to build a self-healing web ring for Bang Bang Con attendees, and like I didn't get it done, but it was the first time I had fun programming in a very, very long time, and so just thank you to all the other organizers again for not listening to me, and for all of the work that all of you have put in. Thank you to all of our attendees and speakers, and I think it is now time for tradition, which is I would like to tell the story of how Bang Bang Con came to be. Cindy, can we put up the slides that I've shared here? So this is the secret after credits. The tag after the credits. This is the origin story of Bang Bang Con. So 2013, so long ago, Maggie Joe, who, as Lindsay mentioned, is our treasurer, asked, are you all coming for Alumni Week to Recurse Center, recurse.com. It used to be called Hacker School, which you'll see that name throughout this. Alex Clemmer, who used to work with us, hopefully, and Ian is like, yeah, I'm trying to work something out. My boss said that if I can find a conference in New York that week that's at least semi-work related, they'll pay for my flight. Potentially. So if we can, let's find a conference this week, this like alumni reunion week, and now Ian gets a free flight. So, okay, so Alex suggests make up a nice conference website, pretend you're going, and then go. Like it's foolproof, right? Just bluff your way through this. So Julia Evans, this is where things start to go off the rails. Says you could organize a real conference by May if you wanted to have no time, probably. And Alex is like, I'll even do it for you. The proto Bang Bang Con is suggested. Julia Evans blog posts con. Allison says I would attend the hell out of that. Is there a call for proposals? And Julia comes up here with the initial call for proposals. Submit a talk. Requirements: must contain at least 3 exclamation marks in the title. Exclamation mark con. Really? Exclamation mark, exclamation mark, exclamation mark con. We now only require one exclamation mark in the title, so really our bar has lowered a lot since this. Maggie pronounced Bang 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 Con, and Julia says, I would actually go to this conference, and here you are. All right, Bang 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 Con needs a website. Ian, thank you, Ian, suggests Bang Bang Con. Here we are. A little easier to pronounce. What should the domain be? Oh, bangbangcon.com is available, I think. Yes, it is. Great. And we need space and a chair. Here's our second draft of the CFP. I won't read the whole thing. But importantly, right, your talk has to be programming related and have an exclamation mark in the title. And originally, we encouraged kind of BuzzFeed Upworthy style submissions, right? You won't believe this one weird GCC bug, and I think we still had a couple of we've had a couple of those talks. Okay, I got carried away. Sad face. I'm not allowed to organize. Julia, I believe at the time you were organizing like 2 other conferences or something like that. So it was like, all right, but we can't actually do this. We can't actually make Bang Bang Con. This is just silly. We're just trying to get Ian to New York, right? Or like on his company's dime. That's the entire purpose of this conference. All right. Alex Clemmer. Okay, Bang Bang Con is easier to say. Registering it. Are we going to have tracks? Should we have talk categories? Right? Like we're rolling with it. All right, Bang Bang Con is in my cart. Registration is imminent. Like, anyone want to speak up? All right, great. Okay. 5 years? 5 years. I'm confident. We have now renewed our domain name. This is, of course, our 7th, I believe, year of Bang Bang Con. 8th year. I'm sorry. Our 8th year of Bang Bang Con. So another 2 years, I believe, and we'll have to renew again. I am now the proud owner of bangbangcon.com. Amazed. Wow. Wait. Did I just register bangbangcorn.com with an R by mistake? Oh, everybody loses it. So yes, we were called bangbangcorn.com. I'm now realizing that we should have really leaned into that with the popcorn emoji and thing like that, but we didn't. We did use Bang Bang Corn LLC as our kind of like backing organization, which was great. I remember we got a check from Comcast one year, and I was like, somebody at Comcast had to like sit down and write out a check to Bang Bang Corn. That's great. I love that. Nick, who's one of the organizers of the Recurse Center, NEA Hacker School, said, we'll host you, but you have to do all the work. And the deal was sealed. So that's it. That's 8 years ago. That's our origin story. This was all a joke that got way out of hand. And here's kind of where you can find us. bangbangcon.com, of course, is our website. Hashtag virtual bangbangcon. Twitter, we are at bangbangcon. We do a lot of our announcements there. And then, of course, I believe Lindsay mentioned that we also the actual like LLC corporation thing behind both Bang Bang Con and Bang Bang Con West is called !Foundation, and that is also our domain name. You can find us at https://
We're not an LLC. We are a nonprofit entity.
Oh, I'm sorry. Excuse me. We are a nonprofit entity. Not a 501c3.
Not a 501c3. Right.
Right. We can't. We're not tax deductible, but we are a nonprofit. So it's kind of the worst of both. No, just kidding. Yeah, we don't. We the organizers don't really make any money off of this. This is all just we're all volunteer. This is all entirely a labor of love for Bang Bang Con. All of the money that goes into Bang Bang Con goes back into making this happen and making sure that we're accessible, making sure that we can, do things. The Exclamation Foundation in our, I don't know if it's in our official mission or not. I should know. I'm on the board. But one of the things that we like to do through the Exclamation Foundation is help other people start Bang Bang Con style conferences. So if you are interested in starting a conference about anything, but particularly about joy, excitement, or surprise of programming, computing, etc. For example, I believe StarCon. That's the only one that's coming to mind right now.
Enthusiastic.
HelloCon, EnthusiasticCon. We just have so much love for those organizers. It's Bang Bang Con style talks, and we would love to help more of these get started. So please reach out to us, through any of these channels, if you're interested in just talking with us, or if you have ideas for Bang Bang Con. For example, the idea to have non-talk talks, musicals and things like that, was an outside idea that came to us. Thank you, Simona. And so, please let us know. Oops, wrong way. There we go. Thank you. That is it for Bang Bang Con 2021. After this, we have a unconferencing session. More details will be in our Discord, and then that'll just kind of turn into people hanging out. We'll all be around on Discord and Twitter. Please ping us. But that's it for the live stream. Thank you all again so much, and we will hopefully see many of you in person next year. So, bye.
Bye, everyone.
See ya.
Mm.